Hello once more, and thanks for coming back here for our IGCSE Math series. According to the IGCSE Mathematics curriculum, 0580. This is the second section of Chapter 8, in which we will discuss different types of probability events and probability calculation methods and cover topics 8.3 through 8.6 of that chapter. Let's get some more information about the different types of probability events. We will start by discussing simple and compound events. In probability, simple events are the most basic type of event. A simple event, in fact, is any event that consists of a single point in the sample space. For example, rolling a fair six-sided die and getting a 4. Compound events, on the other hand, are events that involve more than one possible outcome. They are made up of two or more simple events. For example, rolling a fair six-sided die and getting an odd number. An impossible event is an event that cannot occur in a random experiment. It has a probability of 0. For example, rolling a six-sided die and getting a number greater than 6. A sure event, on the other hand, is an event that is certain to occur in a random experiment. It has a probability of 1. For example, rolling a six-sided die and getting a number between 1 and 6. The complement of an event is simply the probability of the opposite outcome happening. In fact, for every event A, there is another event known as not A or A complement, which we denote as A prime, which represents the remaining elements of the sample space S. Since the sum of the probabilities of all the outcomes in the sample space is equal to 1, we can say that the probability of event A plus the probability of its complement is equal to 1. In other words, the probability of not A can be calculated as 1 minus the probability of A. Understanding complementary events is important in probability because it can help us find the probability of an event by looking at its complement instead. Sometimes, it is easier to find the probability of the complement event and subtract it from 1 to find the probability of the event we are interested in. Let's look at an example to better understand this. Consider the experiment of throwing 2 dice and calculating the possibility of obtaining 2 different scores. The sample space of this experiment can be represented as the set of all possible pairs of scores obtained from the 2 dice. As shown in the diagram, this set contains 36 outcomes as a result of multiplying the 6 possible outcomes for the first die by the 6 possible outcomes for the second die. To get the probability of the event A, we need first to list all the possible outcomes for the event A, which will be a long list. On the other hand, there are significantly fewer outcomes in the event not A. In fact, there are only 6 outcomes in not A, which correspond to the pairs 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6. As a result, the probability of not A is 6/36, or 1/6. Now, we can find the probability of event A by subtracting the probability of event not A from 1, which gives us 1 minus 1/6 equals 5 sixes. As you can see, using the complement can simplify the process of finding probabilities in certain situations. Let us now discuss the 3 main types of probability events. Independent events, dependent events, and mutually exclusive events. Let's take a look at each of them. Independent events are events that have no influence on each other. In other words, the occurrence of one event does not affect the probability of the other event occurring. For example, rolling a die and getting a 3 has no effect on the probability of flipping a coin and getting heads. The probability of getting heads when flipping a coin remains 50% regardless of whether you roll a die and get a 3 or not. The same every time a coin is tossed, there is a 50% chance of getting heads regardless of what happened in the previous trials. However, if you are interested in the probability of getting 2 consecutive heads in coin tossing, then you are considering a different experiment, which is the experiment of tossing the coin twice, not the experiment of tossing the coin once and checking the outcome. In fact, when we discuss combined probabilities, we will go over such a probability calculation in greater detail. Dependent events are events where the probability of one event happening affects the probability of another event happening. In other words, the probability of the second event is dependent on the outcome of the first event. Let's consider an example to better understand this concept.
Suppose you have a bag of 5 marbles, of which 3 are red and 2 are blue. If you randomly select one marble from the bag without replacing it, what is the probability of selecting a red marble on the second pick?
To begin, we will define the events we will be working with. Let B1 and R1 represent the event of picking red and blue marbles in the first time, respectively. And R2 represent the event of picking up the red marble in the second time. As shown in the drawing, the probability of event B1 is 40% and the probability of event R1 is 60%. However, the probability of event R2 is determined by the outcome of the first pick. Therefore, we can say that the probability of event R2 is 75% if the first pick was a blue marble. In fact, we can write this probability statement using the conditional probability symbol, which is a vertical bar between the two events, and pronounce as the probability of event R2 given event B1, which means the probability of event R2 if event B1 has already happened. This is known as conditional probability, which we will discuss in more detail later. Also, we can say that the probability of event R2 equals 50% if the first pick was a red marble, and we can write it using the conditional probability symbol and read it as the probability of event R2 given event R1. Now it is obvious that event R2 is a dependent event because the probability of event R2 is dependent on the outcome of another event, which is the first pick. Mutually exclusive events are events where the two events cannot happen at the same time. An example: when rolling a dice, the events getting an odd number and getting an even number are mutually exclusive because you can't get both an even number and an odd number at the same time. We now have a good understanding of independent, dependent, and mutually exclusive events, but often in real life, we encounter probabilities that involve more than one event. In such cases, it is crucial to understand how these events can combine. This leads us to 3 important concepts in probability: the conditional probability, the multiplication rule for and probability, and the addition rule for or probability. Let's go over those 3 concepts one by one by calculating the probability of different cases based on that example.
In a class of 60 students, 40 are enrolled in a mathematics course, 30 are enrolled in a biology course, and 20 are enrolled in both. What is the possibility that a student is chosen at random? 1. The student is enrolled in mathematics if the student is already enrolled in biology. 2. The student is enrolled in both subjects. 3. The student enrolled at least in one of the subjects.
Let's start by assigning the letter M to the event of a student enrolling in a mathematics course, and the letter B to the event of a student is enrolled in a biology course. In fact, The first request in this problem is a classic case of conditional probability, because we want to know the possibility that a student is enrolled in the math course if he is already enrolled in the biology course, and we can express it in mathematical notation. We write it like this, which we read as the probability of event M, given event B, which means the probability of event M, if event B, already happened. Let us use the Venn diagram to try to solve this problem. Begin by drawing a rectangle to represent the sample space S of the 60 students. Then, inside that rectangle, draw a circle to represent the 30 students enrolled in the biology course and another circle to represent the 40 students enrolled in the math course, and these two circles must intersect because there are 20 students enrolled in both subjects. Let us count the number of students in each Venn diagram section. We have 20 students enrolled in both subjects. 30 minus 20 is equal to 10, students study only biology. 40 minus 20 is equal to 20, students study only math. And 60 minus the total of 10 plus 20 plus 20 equals 10 students do not study either subject. The chosen student is definitely a part of that group because he or she is already enrolled in biology. And for the student to also be enrolled in math, then the student must be one of the 20 students who are enrolled in both subjects. As a result, the probability of that student enrolling in the math course if he or she is already enrolled in the biology course is 20 divided by 30, or 2/3. In fact, calculating the conditional probability with a Venn diagram is part of your IGCSE Math 0580 probability extended curriculum. However, before we move on, I would like to draw your attention to a special case, when the two events are independent, which means that the probability of one event is unaffected by the outcome of the other. If events A and B are independent, the probability of A given B equals the probability of A. For example, regardless of the outcome of the previous die roll, the probability of getting heads when flipping a coin is always 50%. The second request of that problem is a classic case for applying the multiplication rule for n probability, which we write using mathematic notation as, which we read it as the probability of M and B. Let's first solve the problem using the Venn diagram before we talk about that rule. Since there are 20 students who study both subjects, then the probability of M and B is equal to 20 divided by 60, which is equal to 1/3. The multiplication rule for the AND probability deals with finding the probability of two events occurring together. The AND rule states that for any events A and B, the probability of A and B occurring together is equal to the probability of A given B multiplied by the probability of B. In fact, there are two special cases for this rule. If events A and B are independent, then the probability of event A will not be affected by the outcome of event B. Therefore, the probability of A given B will equal the probability of event A. As a result, the probability of A and B will be equal to the probability of event A multiplied by the probability of event B. The other case is when events A and B are mutually exclusive. In this case, event A and event B cannot happen at the same time, so the probability of event A happening if event B has already happened is 0. As a result, the probability of events A and B being mutually exclusive will be equal to 0. Also, we can rearrange the AND rule to calculate the probability of A given B, which is equal to the probability of A and B divided by the probability of B. Let us apply that rule to our problem. The probability of M and B equals the probability of M given B multiplied by the probability of B. The probability of M given B is the probability of a student enrolling in math if the student is already enrolled in biology, which equals the 20 students who enrolled in math and biology divided by the 30 students who enrolled in biology, multiplied by the probability of B, which equals the 30 students who enrolled in biology divided by the 60 students in the class. Before we move on to the next step, I want you to prove that rule, and as a hint, use the n of s to represent the total number of outcomes within the sample space, the n of A, to represent the total number of possible outcomes of the event A, n of B, to represent the total number of possible outcomes of the event B, and the n of A intersection B, to represent the total number of possible outcomes if the events A and B happen together. The third request of that problem is a classic case for applying the addition rule for or probability, which we write using mathematic notation as, which we read it as the probability of M or B. Let us first solve the problem using the Venn diagram before we talk about that rule. Because we are interested in either or both events happening, so we are looking at the probability of any outcomes from that area. As a result, the probability of M or B will be equal to the total of 20 plus 20 plus 10 divided by 60, which gives us a probability of 5/6. The OR rule states that for any events A and B, the probability of A or B occurring is equal to the sum of their individual probabilities minus the probability of A and B occurring together, which is equal to the probability of their intersection. If A and B are mutually exclusive, then the probability of A or B is equal to the sum of their individual probabilities. Since the probability of A and B equals to 0, because A and B cannot happen together. Here is a proof of that rule, please check it out. To summarize what we have learned about combined probability. The AND rule states that for any events A and B, the probability of A and B occurring together is equal to the probability of A given B, multiplied by the probability of B. If A and B are independent events, then the probability of A and B is equal to the product of their individual probabilities. Since the probability of A given B is equals to the probability of A, because the probability of A is independent of the probability of B. If A and B are mutually exclusive, then the probability of A and B is equal to 0. Since the probability of A given B equals to 0, because A and B cannot happen together, we can rearrange the AND rule algebraically to solve for the conditional to get the probability of A given B equals the probability of A and B divided by the probability of B. The OR rule states that for any events A and B, the probability of A or B occurring is equal to the sum of their individual probabilities minus the probability of A and B occurring together, which is equal to the probability of their intersection. If A and B are mutually exclusive, then the probability of A or B is equal to the sum of their individual probabilities. Since the probability of A and B equals to 0, because A and B cannot happen together. In the following slides, we will practice applying these rules to solve problems and deepen our understanding of how to use them in different scenarios.
Before you move on to the solution, please pause the video, read the problem, and attempt to solve it on your own. This will help you better understand how to apply the rules we have just learned.
Let us assume the probability of the yellow outcome is X. Based on the information given, the probability of the green outcome will be equal to 2x. Since the sum of the probabilities of all outcomes in an experiment is 1, we can set up an equation. 2x plus 0.2 plus 0.1 plus x plus 0.4 is equal to 1. Simplifying this equation, we get 3x plus 0.7 is equal to 1. Solving for x, we get x equals 0.1. Therefore, the probability of the green outcome will be 2x equals 0.2, and the probability of the yellow outcome will be x equals 0.1. Since the spinner landing on green and the spinner landing on blue are two mutually exclusive events, the probability of either green or blue occurring is equal to the sum of their individual probabilities, which is 0.2 plus 0.1 is equal to 0.3. To find the probability that the spinner does not land on yellow, we get the probability of the yellow complement, which equals 1 minus the probability of yellow. Plug in the numbers, and the probability of not landing on yellow will be equal to 1 minus 0.1, which equals 0.9.
Before you move on to the solution, please pause the video, read the problem, and attempt to solve it on your own. This will help you better understand how to apply the rules we have just learned.
Let's recall the formula for conditional probability. The probability of A given B equals the probability of A and B, divided by the probability of B. Now, let's apply this formula to the problem at hand. Let event A be the event that someone prefers coffee, and event B be the event that someone prefers tea. Using the information provided, we know that the probability of A and B, that is, the probability that someone likes both coffee and tea, is 50 out of 500, or 0.1. We also know that the probability of event B, that is, the probability that someone likes tea, is 200 out of 500, or 0.4. Plugging these values into the conditional probability formula, we get the probability of A given B equals 0.1 divided by 0.4 equals 0.25. Therefore, the percentage of people who like both coffee and tea among those who like tea is 25%.
Before you move on to the solution, please pause the video, read the problem, and attempt to solve it on your own. This will help you better understand how to apply the rules we have just learned.
Let R1 be the event of getting a red marble on the first draw, and B2 be the event of getting a blue marble on the second draw. Because we have 7 red marbles inside a bag of 15 marbles, the probability of event R1 is equal to 7 divided by 15. After taking out the red marble for the first time, there are 5 blue marbles remaining in the bag of 14 marbles, so the probability of B2 given R1 is equal to 5 divided by 14. Now, by applying the AND rule, we get the probability of event R1 and event B2 equals the probability of event R1 multiplied by the probability of event B2 given R1. Plug in the numbers we get. The probability of events R1 and B2 is 7/15 multiplied by 5/14, which equals 1/6. The tree diagram is a visual tool that helps us understand and calculate the probabilities of multiple events happening in sequence or at the same time. It is particularly useful in probability theory, where it can help us see complex relationships between probabilities by breaking them down into simpler relationships. The starting point of the tree diagram is called the root node, which represents all possible outcomes of the random experiment we are analyzing. It has a probability of 1 because it includes all the possible outcomes. As we move through the tree diagram, we come across stages of mutually exclusive events represented as nodes. The nodes in each stage are referred to as sibling nodes. The siblings' nodes on each stage are considered the children of the previous stage's nodes and the parents of the next stage's nodes. At the end of the diagram, we find the leaf nodes with no child nodes, which represent the final outcomes or events. Each node is labeled with its name. The relationship between nodes is represented by branches, which run from each parent node to each of its child nodes. A fraction, decimal, or percentage associated with each branch in the tree diagram represents the conditional probability of an event occurring at a child node given the event at its parent node. Any event node's probability is the product of the probabilities associated with each branch along the path from the root node to that node. Let us summarize what we learn about the tree diagram. A tree diagram starts with a root node with a probability of 1. Nodes are grouped into stages of mutually exclusive events called sibling nodes. The nodes in each stage are the children of the previous stage and the parents of the next stage. Leaf nodes have no child nodes. Branches are labeled with the conditional probability of the child node given its parent node. The probability of any node in the tree is the product of the probabilities associated with each branch from the root to that node. Because sibling nodes represent events that are mutually exclusive, we add their probabilities to determine their or probability. Let us solve a simple problem to see how the tree diagram can help us solve a complex probability problem.
As a dog owner, you want to take your dog for a walk at night. The weather forecast indicates a 30% chance of rain. If it doesn't rain, there is a 90% chance that you will walk the dog. However, if it rains, there is only a 10% chance that you will walk the dog. What is the probability that you will walk your dog at night?
When we need to use a tree diagram to solve a complex probability problem, we work backwards from the end goal, which is to find the probability of walking the dog at night, and that will be the leaf nodes. The stage before that will be the event that leads to this outcome, which in this case is the weather condition, and because no other event led to the weather condition, the node stage before the rain and no rain nodes will be the root node. Now let's start by building the tree diagram. We start with the root node, which represents the beginning of the event. Then we draw two branches from the root node, one for rain and one for no rain. The rain branch has a 30% probability, which means there is a 30% chance of raining. The no rain branch has a 70% probability, which means there is a 70% chance of not raining. Next, we draw two more branches from each of the rain and no rain branches, one for walk and one for no walk. These branches show what we will do depending on the weather. If it rains, we have a 10% chance of walking and a 90% chance of not walking. If it does not rain, we have a 90% chance of walking and a 10% chance of not walking. Now we have four final outcomes: rain and walk, rain and no walk, no rain and walk, and no rain and no walk. To find the probability of any outcome, we multiply the probabilities along the branches that lead to it. However, because we are interested in the probability of walking, we calculate the probability of rain and walk as 0.3 times 0.1, which is 0.03, and the probability of no rain and walk is 0.7 times 0.9, which is 0.63. To find the probability of walking, we add up the probabilities of the outcomes that involve walking, which gives us 0.03 plus 0.63, which is 0.66. Therefore, there is a 66% chance that we will walk the dog at night. Two-way tables, also known as contingency tables or frequency tables, are a powerful tool for organizing and analyzing data related to two different variables. By providing a clear visual representation of data, they enable us to identify patterns, relationships, and probabilities between two variables. For example, this two-way table displayed data on the favorite type of music and gender of a group of 120 students in a high school. So, the two variables of that table are the student's favorite type of music and the student's gender. As you can see in that table, the student's favorite type of music classified based on the survey data into rock, pop, hip-hop, and country and displayed in the topmost row. On the other hand, the gender variable classified into male and female and displayed on the leftmost column. In fact, you can rearrange the table by displaying the student's gender in the top row and their favorite type of music in the left column. Either option is acceptable. The sum of each column is shown in a row at the bottom of the table, and the sum of each row is shown in a column on the right. And the cell at the bottom right corner of the table displays the grand total, which is the sum of all the cells in the table that represent the number of survey participants, in our case, the 120 students. The number in each cell represent the frequencies or the counts for each category combination. For example, we put 15 in the cell where male and rock meet because there are 15 male students who like rock music. Let's check out how to calculate probability using the two-way table.
What is the probability that a randomly selected student is female and likes hip-hop?
We can find this by dividing the number of female students who like hip-hop by the total number of students in our sample. 10 divided by 120 equals 0.083 or 8.3%.
Excuse me, but how can we be sure that the survey results are accurate for the entire school population? And based on that, we drew our conclusion. For example, if the survey is conducted among students who attend specific music clubs, then the data in the two-way table will only represent those students and not the entire school population.
That's an excellent question. In general, when dealing with two-way tables, unless otherwise stated, you should assume that the table data is a fair representation of the population. Actually, in the next topic, we'll learn how to determine whether the recorded data is a fair representation or not, but for now, let's stick with the two-way table.
What is the probability that a randomly selected student likes hip-hop?
We can find this by dividing the total number of students who like hip-hop by the total number of students in our sample. 35 divided by 120 equals 0.29 or 29%.
With only 3 flavors to choose from, the ice cream seller keeps track of how many of each flavor he sells and displays the results in this two-way table. Someone was seen purchasing ice cream. Calculate the probability of the following happenings. 1. That person was a child. 2. That person purchased chocolate ice cream. 3. That person was an adult who purchased chocolate ice cream.
Before you begin working with a two-way table, make sure the column and row totals are included. If they are not, add them. This will make your calculation easier. Also, before using the two-way table to calculate the probability, please double-check your total calculation. Experimental probability, also known as relative frequency, is a way to calculate the probability of an event based on the actual results of an experiment or series of trials. It is calculated by dividing the number of occurrences of the event by the total number of trials conducted. Assume we are running an experiment to determine the probability of rolling a 6 on a fair 6-sided die. We all know that the theoretical probability of rolling a 6 is 1/6, so if we roll a die 60 times, we should expect to get a 6, 10 times out of 60. To calculate the experiment probability, we would roll the die 60 times and keep track of how many times we got a 6. Let us say we roll the die 60 times and get a 6 on 12 of those rolls. We divide the number of times we got as 6, 12 times, by the total number of rolls, 60, to calculate the experimental probability. This gives us 1/5, which equals 0.2 or 20% experimental probability. If we repeat the experiment many times, each time rolling the die 60 times and recording the number of times we get as 6, we would expect the experimental probability to converge to the theoretical probability. To summarize, the relative frequency, also known as the experimental probability, is the probability of something occurring based on the outcomes of an experiment or a series of trials. It is calculated by dividing the number of times an event has occurred by the number of trials completed. The expected frequency, on the other hand, is the number of times we believe something will occur based on how likely it is to occur. With a large number of trials, the relative frequency should approach the theoretical probability. In the following video, we will go over Chapter 9, which is about statistics. Stay tuned for that. See you soon.